Hello everyone. So today we're going to go over section 4.7, solving counting problems. So when we are solving counting problems, it is very important to establish whether or not order plays a role in the situation. If it does, then we use permutations. And we use combination when orders do not matter. So we'll begin with example number 1. It says that a piano teacher is having a photo taken with her students, and in the photo, the classical students are to be sat together, and then the jazz piano students are going to be seated together. So we can see that in the first part of the question, we have 3 groups: teacher, classical, and then jazz. And there are 3 factorial ways to arrange these 3 groups. So there are 6 arrangements for the groups. Now, of course, there's only one factorial, or one way to arrange the teacher. There are 3 factorial, or 6 ways to organize the classical students. And finally, there are 5 factorial, or 120 ways to organize the jazz students. When this is all taken into account, we have 6 arrangements for the groups, 1 arrangement for the teacher, 6 arrangements for the classical students, and finally 120 arrangements for the jazz students. And if we multiply these 4 numbers together using the fundamental counting principle, we will have 4,320 ways for this photo to be taken. Let's move on to example number 2. So this is a question about cases. So first we have the word oranges, and we're going to arrange the letters in the word with no restrictions. So there are 7 letters. So 7 factorial is 5,040 ways to arrange the 7 letters in oranges. If the first letter must be N, then we have 6 letters remaining. So we will just have 6 factorial, which is 720 ways to arrange the letters. Now, if the vowels must be together in the order O, A, and then E, there's only one way to write the vowels together. What is also important to note is there is one group of vowels and then the 4 remaining letters. So we are actually arranging 5 objects. The group of vowels and then the other 4 letters. So that means we're actually looking at 5 factorial, which is 120 ways to arrange the letters so that the vowels are together in the order O, A, and then E. For this next try question, very similar. So we're looking at the word brains. Now, if the two vowels are together, there are two factorial ways to arrange them. Now, this group of vowels can be arranged with the remaining letters. There are 4 of those. So the second part of the question, we have 4 consonants plus the group, and that gives us 5 objects to arrange. Which means we have 5 factorial, which is 120 arrangements. And finally, using, once again, the fundamental counting principle, we have 2 for the 2 different arrangement of the vowels, times 5 factorial, which is 120. So that's the group of vowels plus the 4 consonants. And once we multiply those together, we have 240 ways to arrange the letters. Now, next set of questions are about deck of cards. So a standard deck of 52 playing cards with 4 suits and then 13 cards each. So the first part of the question asks how many different 5-card hands are there. So this one, all we are looking at is that there are 52 different cards. I'm going to choose 5 of them. The orders do not matter, so this is a combination question. So this is 52 over 5, 52 factorial over 5 factorial times 52 minus 5 factorial. This could be simplified, or we can just use a calculator. Either way, we get 2,598,960 different hands that are possible. Now, next one. Similarly, we are once again looking at 5-card hands, but now they must be all hearts. There are 13 hearts. We're going to choose 5 of them. So very similar to the last one, 13 factorial then, over 5 factorial. This time is going to be 13 minus 5 factorial. We are going to get a much smaller number. It's just going to be 1,287 hands. Next, we are looking at the 5-card hands with all face cards. There are 12 face cards in total. 3 in each suit, so 3 times 4. So 12, choose 5. And again, if we use a calculator here, we will get 792 hands. For the next couple of parts, we are going to be using the combination formula along with the fundamental counting principle. So in this first one, we're looking at hands with 3 hearts. So there are 13 hearts to choose from. We're going to choose 3 of them. And then there are 13 spades. We're going to choose 2 of them. Okay, so again, using a calculator, 13 choose 3 is 286. 13 choose 2 is 78. And their product is 22,308 hands. Okay. And now the The last one is phrased a little bit differently. Exactly 3 hearts. So we're going to choose 3 hearts out of the 13. And the remaining 2 cards cannot be hearts. So there are 39 cards in the deck that are not hearts. We're going to choose 2 of them. Just going to go ahead and write that here, that these are not hearts. Very important. So the first part, 13 choose 3, as we've seen before, is 286. And then 39 choose 2 is 741. And the product is 211,926 hands. So that was a quick overview of combination questions involving cards. Okay, next question is still about combination along with the fundamental counting principle. So here it says we are selecting 4 journalists to cover trial. There are 5 junior and 7 senior journalists available, and the group is going to be containing 2 junior and 2 senior journalists. So it's a lot like the previous question. We have 5 junior journalists, sorry. I'm going to choose 2 of them, and then 7 senior journalists. I'm going to choose 2 of them. So that will simply be 5 choose 2 is 10, 7 choose 2 is 21. So there are 210 possible groups. So next we're going to be looking at questions involving cases. So in the first case, we are looking at a 5-member subcommittee out of 11 council members, 5 grade 12 students, 6 students from the other grades. So we want to have at least 3 students from other grades that are not grade 12s. Okay, so there is the first case where there are 3 students from other grades, which means there are going to be 2 grade 12s, so 5 choose 2 for the grade 12s, and then 6 choose 3 for the other grades. We're going to add the second case, which is going to be 1 grade 12 and 4 students from the other grades. And then we have the third case, which is going to be no grade 12, so 5 choose 0, and then 5 students from the other grades out of 6. And here, using a calculator, 5 choose 2 will give us 10. 6 choose 3 is 20. 5 choose 1 is 5. 6 choose 4 is 15. 5 choose 0. There's only one way to choose 0 things out of 5, so that's 1. And then 6 choose 5 is going to be 6. From there, we can multiply everything out. So that will give us 200 plus 75 plus 6, which gives us 281 ways, or forming the subcommittee. Okay, now we're going to go back to the cards once again, but with cases. At least 1 red card here. So for this question, we're going to state the opposite, which is that there are no red cards. And what we're going to do is look at the total that are possible, the total possibilities, and then subtract the one that contain no red cards, which means that the remaining ones must at least have 1 red card. going to go ahead and write that out. So no red cards. Again, first step is to figure out all the possibilities. So that will be 52 cards, and we're going to choose 5 of them. So there are no restrictions here. All the possible hands are to be included here. And then we're going to subtract the hands that have no red cards. So there are 26 cards that are not red. We're going to choose 5 of them. So all of these hands will have no red cards. And the difference is going to be 2,533,180 hands. And these will all contain at least 1 red card, since we have removed all the cases where there are no red cards. Okay, so next one, unfortunately, there is no shorthand for doing example 5b. So we have to look at the statement. It says at most 2 kings. So there are 3 possibilities. Either there are no kings, there's 1 king, or there are 2 kings. Let's go ahead and write that out. So starting with no kings. So there are 4 kings in the deck of cards. We're going to choose 0 of them. That means the 5-card hand is going to have 48 non-king cards, and we're going to choose 5 of those to fill out the hand. Next is going to be the case of 1 king, so 4 choose 1, and then 48 choose 4. And finally, the last case, we're going to have 4 choose 2, so 2 kings, and then of the remaining 48 cards, we're going to need 3 of them. And what we'll do is, well, first go ahead and label what each one of these were. So the first case, no kings. The second part is 1 king. And then finally 2 kings at the end. Okay, so first case is going to give us 1,712,304 hands with no kings. 1 king, that will be 778,320 hands. And finally, 2 kings, just 103,776 hands. And so if we add these 3 together, that will still be 2,594,400 hands. Now the last question is another combination of cases question, but a little bit more general, so it's not confined to a deck of cards. Okay, so we are looking at a subcommittee once again, 6 council members. Now there are 15 council members to choose from, and 6 of which play for a school team. At most 1 school team member, so either 0 school team member or 1 school team member. So there are 6 who play from the school team. Either we choose 0 of them, which means all 6 members of the subcommittee is going to come from the other 9 members. Oh, sorry about that. That is supposed to be multiplied together. Or the second case is if there is a single school team member, and then the other 5 subcommittee members will not belong to a school team. Just like so. The first product here is 84, and the second product is 756. So if we add those together, there are 840 possible subcommittees, or 840 ways to form the subcommittees. Right, so today was a quick overview of permutations and combinations and the kind of questions that we can be asked or look at. And that's it for today. So once again, thank you for listening.